Welcome, everyone. My name is Nathan, and I'm joined by my colleague, Daniel Moyer.
Hello, everyone.
Welcome. Good morning. We're glad you've joined us for today's webinar. We will be conducting a training. It's a NABCEP certified training on the functionality of battery management systems, as well as providing the details in this training about how our battery management systems work and function with our various battery products. Give just a couple of minutes for people to trickle in. As I mentioned, this is a NABCEP certified training. You can receive 1.5 hours of NABCEP credit, and we will provide our email address at the end. Thank you for your attendance. I also want to mention that there is a Q&A session, and you should be able to find that where your Zoom menu appears. Daniel will be monitoring the Q&A and providing answers to some of those questions. And Daniel, feel free to interrupt me at any time if we have a question that should be answered live.
Of course. Thank you, Nathan.
Okay, so the details of this class, the things that we're going to hit are highlighted here on this screen. We're going to talk about what is a battery management system and what it does. What does it do? We'll talk about some UL standards regarding BMS. We'll talk about why battery management systems are so vital to lithium-ion battery performance and safety, why they're necessary in batteries. We'll also talk about how the AmpliPHI BMS uses closed-loop communications and how you can use that with compatible equipment. We'll talk about when to use the PHI BMS with different voltage set points for compatible equipment with that as well. That is an inverter agnostic battery that we sell, so we'll get into the details of how that battery functions and equipment that's good to pair with it. We'll also talk about sizing your battery bank to meet project and customer objectives, and integration with inverter charge controllers that can be used with AmpliPHI PHI, SimpliPHI batteries, essentially our battery lineup. So again, Energy Made Simple. This is Briggs Stratton. What you're seeing on the screen in the background is a marketing picture noted showing our inverter with 3 of our 4.9 batteries. These are our outdoor rated wall mountable batteries, and they will be covered in this training as well. If you're interested in free training opportunities, I encourage you to register for the Briggs Stratton Power Academy. On the Power Academy, we have in-person courses that are scheduled, and so you can join some of them. Daniel, you'll be teaching a course in New Hampshire just at the end of the month.
Yep, exactly. And I just want to mention, everybody, the Power Academy is not just for in-person. There's a lot of e-learning on-demand courses. So if you can't make it to a specific time, this is a great platform. Anybody can join. If anybody has trouble, let Nathan or I know, and we can help you get in.
Exactly. And the on-demand courses within the Power Academy let you go at your own pace, so you can register for these courses and learn. We have courses on our generators, and we're increasingly putting more and more content onto the Power Academy. Additionally, we have more webinars coming up in January next week. I'll be speaking about whole home backup featuring the SolarC 15K with our batteries. We have another training at the end of the month on battery energy storage with generator integrations. And I know that's a popular topic, both for off-grid, but also for customers that have frequent outages and that really want to have that generator for those long-term outages. We are one of 2 manufacturers in the US that manufactures both generators as well as batteries. Daniel, you're going to be going to Intersolar next week.
Yes, and really looking forward to it. If anybody on this webinar is going, just go ahead and put it into the Q&A. Let me know you're going, because I'd love to see you there. Nathan, can you actually go back one slide?
Sorry about that.
We're going to be at booth 2835. If anybody is interested in going, there is a QR code right there for a free pass. Now, it's not a full conference pass, but it is an expo pass that will allow you to walk the floor and come say hi to us. So if you're going, please put it into the chat. I'd love to connect with you. Next, please, Nathan.
Yes.
In the booth, we are going to be doing in-booth training. And one of the really most exciting parts of that is we're going to be having a new battery coming out. And Nathan and I can't talk about a lot of it right now. We'll be able to talk more about it after we've introduced it. But come to the show, take a look at this new product. Other ones, we're going to do abbreviated versions of that generator talk, talk a little bit about the future of NEM 3.0, some commercial industrial. We're going to have coffee at the booth on Wednesday and Thursday morning. please let us know if you're coming. I'd love to see you there.
And we'll have a very large presence there, right? We will have trainers, we'll have our vice president. We have the president of the Energy Solutions division who's going to be there. We have a large number of people that are there to help you learn. So please do show up. If you're in the conference, we would love to see you at our booth. One more time, that booth is 2835. So one of the things about our batteries, and one of the reasons people choose them, is that we are a trusted brand. AmpliPHI batteries have been around for almost 15 years. We've been a California manufacturer for a long time, making these batteries at our facilities in Oxnard. We've got a 15-year warranty. And Daniel, this is a true warranty, right? We're looking at a 15-year warranty. How does that warranty compare to the competition?
A lot of people have necessarily 10-year warranty, and a lot of them also have a certain number of cycles or a certain depth of discharge or a certain throughput clause, where we're straight 15-year warranty, and we'll honor that. At the end of that time, we warranty a 70% retained capacity. And Nathan, maybe you could speak to a little bit about how batteries lose capacity as they age.
Yeah, sure. And I realize that we need to jump into the content here and speak about the battery management system. And I don't want to spend a lot of time on marketing here, but I do want you to know this is a really solid warranty. We don't have a throughput warranty. We don't limit it to a certain number of kilowatt hours that the battery has charged or discharged, as our competitors do. This is an unlimited number of cycles. It's a 15-year warranty, and we guarantee 70% of that original storage capacity in the battery 15 years from your installation date, right? So it's a really solid guarantee, because we feel that we make about the highest quality battery product there is on the market. And we do a lot of things to ensure that our cells are premium cells, that our BMS takes good care of our battery. And that's the topic today that we're going to jump into in more detail. I highlight here that all of our batteries use LFP battery chemistry. That's lithium iron phosphate. And most of the industry is switching to this now, but we've been doing this since 2010, so for quite a long time. If you are a California installer or even a California homeowner, right, there's an extra 20% discount that you can get, you can apply for from the CPUC. And this is available already on our AmpliPHI and PHI batteries, and we're getting this certification as well for our AmpliPHI 4.9 battery that's there. That's the outdoor rated wall mount battery. So once we get that manufacturer certification, all three of these batteries can earn you an extra 20% discount from the CPUC. Daniel, do you want to speak just a minute about how we apply for that? So we've noted that you can apply for that through PG&E, SDGE, SoCal Gas, Edison.
Yeah, there's a list of approved batteries. So you get onto that list and you'll find our battery, at least the AmpliPHI and the PHI for now, and then you go ahead and use that. And we have team members that can help you navigate any of the complications that you might have going through this process. So reach out to us. We'll have our email here at the end, and we can help you out if you have any trouble applying for this. There's a lot of opportunity to save your customers money and make that sale.
And I also want to mention that the IRA also now includes battery-only installations. You don't have to have them powered with solar panels to get that 30% tax credit as well. So all of these things are making battery systems more attractive. I realize that at least in California, NEM 3.0 has hurt the market to some extent for solar, but has made the case for battery demand even stronger. So what is driving the market, right? What is creating that demand? We'll talk just briefly about this, but essentially more and more customers are wanting their home as a haven. We have people working from home like me, and this has just grown in the past few years, needing to have that reliable electricity, not wanting to lose power, needing backup power, right? We also have aging infrastructure, and aging infrastructure leads to more outages. And then, of course, climate-related disaster is responsible for some of the longer-term outages, the longer duration outages. But it's also a demand thing. More and more people are getting electric vehicles. More demand is on the electric grid. And so this is also a reason for people wanting solar, wanting batteries. Of course, there's also the desire to grow clean energy solutions and policies. Once you get those solar panels on your roof, once you get that battery there in your house, you can make use of clean energy. And so the home battery market is booming. It's expected to reach 6.6 billion by 2027. Currently, only about 1 out of 10 solar owners have battery storage, and that number is projected to increase to 1 out of 3 in the coming years. I point out one more time that AmpliPHI batteries have been around the world for a long time. And so since 2010, we have over 300 megawatt hours installed worldwide, providing backup power to our customers. Batteries give customers a way, most people understand batteries give customers a way to back up their loads, back up their home. But there are also other things you can do with it, such as peak shaving, right? If you use some CTs to monitor the amount of power that you're pulling from the grid, you can get that inverter to discharge those batteries to reduce the amounts, the peaks that you are causing when you pull from the grid. And so that removes some of these charges that utilities are charging once you go beyond a certain threshold in your power consumption. It also allows people to do what's called energy arbitrage by using, if you are in a jurisdiction or if you're on a rate plan that has time of use rates, one of the things you can do with your batteries is you can charge those batteries when it's cheap, and you can discharge those to power your loads when that electricity is expensive. So if you're in a location where during the nighttime electricity is cheap, you can charge up those batteries during the nighttime, and then you discharge them during those peak demand rates during the day. So in my location, the afternoon/evening are excessively high electricity charges. And so one of the ways I can avoid that is to charge at night and then discharge during the day. Now, I don't do that because I actually have solar on my house. And what I do is do the integrated solar plus storage, in that I generate the electricity, more than the electricity than I need during the daytime. And then I discharge my batteries over the course of the night and the next morning in order to just use renewable energy.
Yeah, and that third slide or the third image right there on the right-hand side is really what is happening here in California. It used to be you could use the grid as your battery, right? That purple that you see there, that purple would be sent to the grid. You would get a credit for that in kilowatt hours. You could then use that credit kind of during the green, right? Now, and not just in California, there's a lot of other states, utilities, jurisdictions that are starting to kind of adopt this, and it's really.
I believe Idaho just went to it as well, Daniel.
Yeah, and it's unfair in a lot of ways. This isn't the talk about it, but what we can do is use storage to store that production from solar panels, and then discharge the batteries when you would otherwise be buying power at 20, 30, 40, 50 cents a kilowatt hour, when you would have otherwise gotten paid less than a cent a kilowatt hour in some examples for sending it back to. So it's really important to understand that NEM 3.0, we have upcoming talks. I do want to also encourage I know we're not to the part yet, but anybody who has questions, please put the questions in Q&A, and I'll get Nathan to answer them.
Thanks so much, Daniel. Well, we're going to jump into basic concepts around energy storage systems right now. And I realize that most of you have probably already covered these, but it's also important that you educate homeowners as you do installations on what to expect, on how things work, so that they have a general understanding of what to expect with their energy storage system, especially when the battery storage is involved. There are a lot of misconceptions. I'm going to point out here the typical components of an energy storage system. Not always, but often we have solar power that is coming in to fill up our batteries. This is our fuel source, and the solar panels can be thought of as energy pumps. They're essentially pumping that energy into your inverter, and that can be either sent back out to the grid if there's excess. It certainly can be sent and often is to cover the loads of the house, either critical loads or all the loads of the house. But additionally, if there's excess energy, it's often used to charge a battery. So the idea is to overproduce with the solar during the day, cover your loads, and also cover the charging of the batteries, and then discharge those batteries when you need. As Daniel said, that's become the model. Now, if a grid outage occurs and the solar is not quite enough to keep up, this is much more common with a winter grid outage where you have a lot less available solar because of the shorter days, you might want to include a generator. And as I mentioned before, we do manufacture both generators and batteries / inverters. as well as have a monitoring and control app. And so our generators work together with our batteries, and our app allows us to interface all three, so that if the batteries get down and there is no solar available, the inverter can automatically start that generator up and get those batteries charging and cover those loads if the batteries are low. So let's talk just for a minute about the difference between power and energy. And I know this is quite basic, but again, it's important that a customer understands this. So power consumption by loads measures how fast electrical energy is used. And I like to use a water analogy where you can think of power is a measure of how quickly the water is flowing through the pipes or the electricity through the wires. And this is measured in kilowatts. Other units for this, of course, are horsepower, kVA. kVA is the same thing as a kilowatt. A volt times an amp is a watt. So power is how fast energy is being consumed. Energy is how much, right? How much electrical energy is consumed over a period of time. And it's often measured in units of kilowatt hours. Other units, of course, are calories, joules, BTUs when we're involved with heating and air conditioning. But kilowatt hours is a pretty good measure. And it's easy to use with kilowatts. I mention all this because these, even professionals, right? We often slip up as we're talking about the kilowatts for a battery or the kilowatt hours for a battery. And actually both apply, which is why I'm mentioning it here. And of course, there's that relationship between energy and power, where energy is really the integral of power over time, or more simply put, just power times time. So that if I have 1 kilowatt, that's 1,000 watts. For 1 hour would be 1 kilowatt hour. 1 kilowatt hour could also be 2,000 watts over 30 minutes or half an hour, right? It's the energy is the power times the amount of time that you're using it. So one more time, just to drive this home, this is an example of a solar install that I had done with students some years ago. And what you're seeing here is a water tower and then solar panels on the top, a little over 1,000 watts of solar panels on the top of that tower. And those panels are used with a pump controller, and there's a pump out in the lake pumping water up. So essentially, these solar panels are absorbing energy, and then there's a storage of potential energy in the form of water inside this tank. Well, a battery is very similar to a water tank in many ways, right? So a battery is kind of a tank that holds a certain amount of energy. And most customers realize that a battery has a capacity to hold energy. However, there's also a limitation to how fast that energy can be delivered, how quickly the energy can be taken out of or put into the battery. So there are power limitations to batteries as well. The capacity of the battery will be specified in kilowatt hours, and the output power capacity of the battery can be specified in kilowatts, or often in something called a C rating of the battery, which I'll get into a little bit later. Another analogy here is that the pipes that feed this water tank, we used 2-inch pipes for this particular application. I can only push so hard to put water into that tank without rupturing those pipes. The same thing with electrical wires. I can only push so much electricity out through a wire before I heat that wire up and potentially melt it or destroy its insulation. So I like that analogy, which is why I kept it here.
Nathan.
Yes.
We have a question.
Yes.
Not specific on what we're looking at, but I think it's a great question.
Sure.
Philip's asking, how are electric vehicles related to home battery energy storage systems as a sales point? No one would typically charge an electric vehicle's battery from a ESS battery. What is the presumed advantage? Are the Briggs Stratton inverters rated for vehicle to grid? Now, before you answer, I just want to kind of, I hear this a lot. A lot of people want to use the idea of using an electric vehicle. I do want to point out that, and we pointed this out earlier, is that batteries have a finite number of cycles. And I can see vehicles in certain applications serving as backup. But, you know, I wouldn't want to use up the cycle life of one of my batteries in my car, especially maybe a cobalt chemistry, to do, say, time of use arbitrage. And so can you speak a little bit to how you see the future of electric vehicles interacting with home batteries? And you know, I recognize a lot of people drive during the day and then come home at night. And without being able to have that net metering, speak a little to that. Thank you, Philip, for the great question.
Yeah, it is. It is really a good question, and I wouldn't say that people won't charge an electric vehicle from an ESS system, right? The efficiency, especially of DC coupled solar to batteries, round trip efficiency is around 92%, right? You're not losing a lot of energy. And with our batteries giving you an unlimited number of cycles, a 15-year warranty, 70% guaranteed original capacity remaining after that 15 years, right? You have a lot of cycles in those batteries. 10,000 cycles is 25 years if you do it once daily. So yes, it's an added cost to have a battery backup system at your house, but you're also collecting free energy if you have excess solar in addition to the loads of your house. If you have more solar than you're consuming, well, you get pennies on the dollar if you feed that back to the grid in California now, right? So it would make sense to save that energy and put it into your electric vehicle. Now, the question is how big is that electric vehicle battery, right? So to give an example to this, I have a relatively small 5 kilowatt solar array on my roof. During summer days, I generate on the order of 30 kilowatt hours. Well, a typical electric vehicle, right, has a battery pack on the order of 100 kilowatt hours, small ones at 80, large ones at 120 or larger. And so that 30 kilowatt hours, we're only talking a quarter tank of gas. It's questionable as whether or not you would want to save that up and then use that for your home or your vehicle. But if your home isn't drawing a lot of power, you could send that to your vehicle. But I don't think that's the essence of the question, right? The question is, would we use the electric vehicle to discharge into the house and avoid the purchase of a home battery backup system? Would we avoid the purchase of the ESS? The problem with that is, of course, unless your vehicle is parked at your house during the day, you can't use that energy that's being generated during the day to charge up the electric vehicle. And currently, I don't know of any electric vehicle on the market that's doing vehicle to grid, that's allowing vehicle to grid transitions for energy. That might change. It might be that one company, let's say Ford, goes ahead and says, hey, look, we're going to allow you to use your new electric vehicle to run your home and back up your home, and others might have to follow suit. But currently, it seems that this is only being talked about and not being utilized. And even if we could do that, I still see that value of the home battery backup system, either as an intermediary to discharge into the electric vehicle when the vehicle comes home, or just to provide that additional backup during the day if that electrical vehicle isn't there, some storage place so that you can pump that energy hitting the solar panels. So long-winded answer, and I think the answer is it's uncertain. We don't know what the electric vehicle manufacturers are going to do. Certainly you have a large capacity in those electric vehicles, 100 kilowatt hours, right? And typical home backup systems are on the order of 20 to 40, 50 kilowatt hours, right? Not nearly as big as electric vehicle ones. So back on the theme, I hope I answered. Back on the theme of solar and energy, we're just going to quickly review solar and then jump into batteries, starting from the basics, going through the more advanced features of BMS. Again, this is a 1.5 hour long webinar. We've got about an hour's worth of that BMS content. We will have time for questions and answers at the end as well. But think of the solar panels as energy pumps. They get that solar energy from the sun and they pump it in various directions. They can pump that into the inverter, right, through an MPPT, and that's a device known to maximize the output of solar panels. So if solar panels have a very varying voltage / current curve, if you draw more current out of a solar panel, the voltage will start going down. It goes down very slightly at first, but if you draw the charges out of that solar panel faster than the solar panel is producing them, you get a very rapid drop off of voltage when you're drawing too much. And so there's a maximum power point, which is where that current times voltage is maximum. So current times voltage, as we mentioned before, that's power, that's watts. And there's a maximum where the current is still high, but the voltage is high. If we go too much further, the amount of power drops off. So this blue curve here illustrates that maximum power point. There are devices that are used to track that maximum power point. The Briggs Stratton inverter, for example, has 2 independent devices called MPPTs, maximum power point tracking devices. right? Which are used to take the DC energy from the solar panel, maximize the amount that is being pumped, and push it into the inverter or into the charging system of the inverter. Not all inverters have battery charging integrated into them. The ones that do are called hybrid inverters, and the industry is really going to these all-in-one type units where you have the MPPTs built into the inverter. If you don't have that, you might have separate charging equipment, such as maybe a Midnight Solar charge controller. The Midnight Classic is a good example. Schneider has their independent 600-volt charging system. But a lot of the newer equipment is going with integrated, what we call hybrid inverters. These inverters also allow you to interface with the grid. So here's an example of AC power coming out of inverter from an array that's on the order of 7.5 kilowatts, I believe. And so it's the array shown here. There are 20 sun power panels there. And notice that you have a 7.5 kilowatt array on the roof. Well, that doesn't mean whenever the sun is out, you're getting 7.5 kilowatts. Everybody knows, right? Or most people know that energy profile reaches a maximum. Now, this is taken in late winter, and you can see that the maximum doesn't even hit 6 kilowatts on this particular day. That has to do with the angle and the temperature of the panels. Over the course of the year, of course, there are days when you generate more electricity and days when you generate less. And many customers don't realize that you're going to generate about half the amount of energy in a winter day. This is a January day. We're here in the month of January, and this system is putting out about 20 kilowatt hours over a January day. Whereas at a summer day, you're looking at peaks that are above around 50 kilowatt hours. There's a big variation of how much energy you're generating in the summer versus the winter. And this is more and more drastic the farther north you go, because bigger changes in the length of the days. And of course, orientation of the panels matters a lot. So all of these being said, we're going to go back to that original reason people are using batteries and talk about it in a little bit more detail. If you had a home which was only consuming on the order of a kilowatt of energy, let's say on average, if you put a 1 kilowatt solar system in there, or maybe a 1.5 kilowatt solar system, it would probably max out and supply your loads for just a short, maybe 3 or 4 hours during the peak of the day. So what we do instead, of course, is oversize the solar system to cover more than the loads of the home. Use the battery to save this extra energy, all this extra energy beyond what the loads are consuming, is indicated by this dashed line. And the area under this curve here, is the amount of energy that we would get in kilowatt hours. Again, power times time is area, and that would be the area here. That would be the energy we would save, and then try to use that energy here in the evening and then in the morning. And so you oversize your system. Well, you do that with batteries. So let's get into batteries. That's why you're here, is to learn about battery management systems. Well, chemistry and form factor play a big role. A lot of people say lithium battery and they think it's all the same, right? But they're not all the same. There are different battery chemistries. There are even power cells versus energy storage cells, right? Power cells are designed to deliver that energy really fast, discharge and at a rate called 20C. That means in 5 minutes. So there are different chemistries. There's a lithium cobalt oxide, nickel, manganese cobalt oxide, manganese oxide. These NMC cells are very common. And in fact, many of the electric vehicles, especially the early ones, were made with NMC cells. Now, the LFP cells, just because their increased lifetime and their increased lifetime and their durability and their safety, more and more car manufacturers are manufacturing with LFP. And so if you have a newer Tesla or a Rivian, for instance, you're most likely driving with LFP battery chemistry. It's a safer battery chemistry in the event of a car crash. It's a little bit heavier. It's true. You get a little bit less mileage, but you also get a battery that lasts a few more years. The longer lasting battery has more overall value at end of life compared to those NMC. So it won't die quite as quickly. Of course, there's some other batteries as well: nickel, cobalt, aluminum oxide. I've even put lithium titanate on here. Lithium titanate involves using a different anode. All these other batteries use a different, what's called cathode, and I'll say what that is in just a minute. There's some values to the other batteries, but again, we really feel that the mass manufactured battery on the market is LFP. That's the best lithium battery that's out there right now. We've got many years, well over a decade of experience producing batteries with the LFP battery chemistry. But not only does the battery vary in terms of chemistry, it also varies with how they're constructed. And the best type of construction is this cylindrical cell. We use cylindrical cells because they're the longest lasting, most durable, and highest quality cell you can get. They are more expensive. And there are alternative versions such as a pouch cell or prismatic cells. Pouch cells are typically encased in an aluminum foil where you have sheets of positive and negative material, the cathode and the anode, that are sandwiched inside that pouch, and the electrolyte is backfilled in there as well. Now, there have been a lot of advances on pouch cells, and they're getting better and better. I hear more and more about BYD's blade batteries, etc. There's also a type of cell, a form factor called prismatic. So a prismatic cell still has some problems with swelling, with temperature variations. The reason the cylindrical cells are so good is because you've got a rigid cylinder holding the shape of that battery, so you don't get any bulging when the battery heats, etc. The prismatic cells are a plastic cell, but you've got some rigid plastic forming the walls, and so you have less expansion and contraction. Typically, these come in really large form factors, which makes them cheaper to produce. But again, we use cylindrical cells in all of our batteries. And we've been doing so because of the longevity it gives us. It gives us this opportunity to give you a really solid warranty. Additionally, of course, we've got a computer inside of each of these batteries. And that computer was designed here in California, manufactured here. And we've got a really good computer in this thing called the battery management system, which is what we're going to get into. Cell functionality. So if we look at the construction of a cell, again, if there's some point where you don't want to know all these details, just skip over this section here. But I'm going to go ahead and explain what happens inside a cylindrical cell. So inside a battery, you have layers of cathode and anode material. So the positive side of the battery is the cathode material, and that's typically a spray-coated aluminum. So those metal oxides I was talking about are going on top of this aluminum foil, and then that's separated by a separator layer. And on the other side of that is copper, which is typically coated in a graphite or potentially even a graphene. There are advancements being made. And that graphite layer is responsible for being the negative side of the battery. So you've got a positive and negative side of the battery. Look on the right side of your screen now. I'm going to try to explain what happens between these layers when a battery charges. So if you have an uncharged battery and you hook up a charger to the battery, what happens is that charger pulls off electrons from the cathode of the battery, and it pumps them over to the negative side of the battery, the anode. When we pull electrons off of the metal oxide, it liberates the lithium ions that are attracted to that metal oxide. They're embedded within that metal oxide layer, and it allows those lithium ions to be free to move. Well, as those electrons build up on the negative side of the battery, there's an electrical pull drawing lithium ions in. And so what we have is a porous separator layer that prevents solid lithium and electrons from moving through, but it allows ionized lithium without their electrons to move through. And so the separator layer acts as a barrier for electrons, but it does allow lithium ions to move through. And the way we make lithium ions mobile is we embed the whole thing in this organic electrolyte. It's basically a salt solution with lithium ions in it. And so those lithium ions get pulled over and embed themselves in the graphite in a process called intercalation. I'm sorry, I blanked on that. So that intercalation process, it can slow down in cold temperature. I'll talk a little bit about that. But that's a charged battery where we get that lithium to reside on the negative side, the graphite side. In a discharge process, you allow the electrons to flow back to the other side, and that draws the lithium back to the side it really wants to be on. The metal oxide side is more stable there. So that's how a battery functions. Of course, there are problems with batteries functioning, right? You can have an internal short. You could have that Tesla car get into a car accident and the casing gets damaged. And so what can happen if you damage the cells or if some circuit fails, etc., you can have what's called a thermal runaway. And thermal runaway is something where maybe the battery is shorted and that negative anode is in contact with a positive cathode, and you no longer have that separator layer preventing the electrons from moving straight from one side to the other. Well, if something like that happens, you can get this really rapid movement of electrons from one side to the other in a short. or maybe there's a circuit failure which causes a similar short. And when you're moving electricity, right, really rapidly, high currents generate heat that ends up causing a battery cell to heat up. Well, let's suppose that happened inside a cylindrical cell. So I've drawn a couple of cylindrical cells here just as an example. What could happen is that battery could get hot enough that organic electrolyte I talked about could actually create pressure inside the cell. Cylindrical cells are designed to release that pressure through a vent if the pressure gets high enough, on the order of 10 atmospheres, about 10 times atmospheric pressure. And so the pressure gets high enough, it can vent out, and what it does is it releases that organic vapor. Well, if that organic vapor catches fire, it can cause the cells around it to heat up, and they can also off gas. And that's what's known as thermal runaway. So we need to make sure with lithium batteries that we don't have thermal runaway. We have to keep these batteries safe. Many of you have probably seen pictures of lithium battery fires. It's not the lithium that's burning, right? It's the organic electrolyte, that vapor that's coming out of those heated battery cells, which is burning. It isn't organic, and it can combust with oxygen. So this is a danger, and it's very important that we prevent it. Well, one of the reasons we don't use NMC is because NMC batteries are much more prone to thermal runaway. The shorting an NMC battery cell is a much more violent reaction. It releases energy a lot faster than an LFP cell. LFP cells still release energy, but not nearly as quick. So there's some independent, we've shown this video before, we've shown at least these pictures of this video. This is, Will Prowse runs this channel on batteries. I highly recommend his channel. And what he demonstrated is he drilled into a battery. It was labeled as a solid state battery. He had bought it from an Asian supplier. He took it apart. Indeed, it wasn't a solid state battery, which doesn't contain electrolyte. It was a pouch cell with NMC chemistry inside. And he punctured this by drilling through it to see what would happen, more safety equipment. But almost immediately, the battery started spewing out smoke. And then fairly quickly, that smoke caught on fire. And you can see what happens, a very violent release of that energy from the electrolyte burning. Well, he then about a week later, repeated the test. But he did it with an LFP pouch cell. And taking that LFP pouch cell, you can see he had to drill, it was about 10 holes in this pouch cell to even get it to off gas. And so it kind of highlights, and you can see what's coming out there. This is just a little bit of smoke. We never saw flames with this. Again, 10 punctures before this would happen. And you can see other examples of this. That's why we use LFP. It's safe. It's longer lasting. It's the most durable, safest chemistry out there on the market. Again, it's why we chose it 14 years ago. So a couple of other things to point out about the safety. When thermal runaway begins, an LFP battery has to get to a couple hundred Celsius before that even begins. It's on the order of 300 Fahrenheit or so. An NMC battery, right, can go into thermal runaway at a lower temperature, around 170 Celsius, right? And that difference matters, right? It determines the likelihood that your battery might go into, an off-gassing event. LFP batteries also reach a lower maximum temperature than NMC and cobalt-based chemistries during thermal runaway. So again, because the LFP battery is releasing the energy much more slowly over a longer period of time, the overall temperature you get to in a thermal runaway event is on the order of 400 Celsius compared to that of NMC, which is approaching 700 Celsius. Right? So again, these are the reasons why we make our batteries out of LFP. There are advantages to NMC. They're more energy dense, right? They don't weigh quite as much. But for home battery backup, we don't really care about that. We care about the safety. If the battery weighs 100 pounds instead of 80 pounds, it's not a big deal to a homeowner because that battery is just sitting on a shelf. And as I mentioned, it's not even a big of a deal to car manufacturers because the increased longevity, and that's why they've also switched to LFP. Well, an individual LFP cell has a voltage of about 3.2 volts. That measures how much more the lithium wants to be in the LFP side, the ferrophosphate side. That's the equivalent of the metal oxide, our positive side of our cell, compared to the negative side, the graphite side. And so an individual cell only has 3.2 volts nominally. Well, just as to generate a 9-volt battery, you would put 6 1.5-volt cells in series to get that 9 volts out. We do something similar in our batteries. In fact, we have 16 batteries in series, or 16 stacks of cells in series to get up to a 48-volt nominal battery. So we have several hundred LFP cells in a single battery like this. And then, of course, we have a high-performance battery management system incorporated inside here. And the role of the battery management system is what we're going to get into. But we also have, just point out here, there's communications ports. This is for the computer called the BMS to communicate out to other equipment and to things like gateways, inverters, charge controllers. There's also an integrated breaker, so we have the ability to turn this off. Each of our batteries has a 100 amp breaker on it, so the battery can output a maximum on the order of 5 kilowatts before tripping this breaker, around 50 volts times 100 amps before we trip that breaker.
Nathan,
yes.
I want to go back one slide. I want to encourage anybody to put in questions. We really encourage questions. It keeps these talks engaging. I had a question about that 9-volt battery. I'm just now noticing it. Are all of those cells in series, or am I looking at 3 cells in series and then another 3 cells in series that are then paralleled up?
No, these are all in series. You can't see all the connections, and so possibly I should have chosen a different. These are alkaline cells, which have a nominal voltage of 1.5 volts.
Thank you.
And so you're going from the negative of one cell to the positive of the other. And if on the bottom of that, you would see this going to the bottom of this cell, it goes up, it goes across the top here, down to the bottom, over to the bottom and across. And so these are all in series there. So
yeah, I was thinking 3.2 volts. That's a little more than 9 volts.
Yeah, my apologies. LFP cells have a nominal voltage of 3.2. Alkaline batteries have a nominal voltage of 1.5. Okay, so what is a battery management system, right? It's the brain of a deep cycle lithium battery. A BMS is what protects the battery. It's what communicates out to equipment, and it's got different roles, right? So the major role of a BMS is to protect the battery from functioning outside its safe operating parameters. It can also monitor various environmental and system-based conditions, such as the voltage of the charge controller. So if you have a malfunctioning charge controller, the BMS can shut down that connection to the charge controller and protect itself. It can monitor cell temperature. If the battery cells get too hot, it can slow down the discharge rate or the charge rate. It can monitor the amperage and make sure that amperage doesn't exceed what the battery can handle. And it also, a big function of a battery management system is to maintain state of balance. And what that means is keeping all of those 16 stacks of series cells balanced so that they're at very similar states of charge. A chain of battery cells in series is only as strong as the weakest link, right? The battery with the least amount of energy in it. It will discharge first, right? And so we want to keep them all balanced so they have same states of charge. It also allows, in some cases, for programmable communications, and so the opportunity to be able to program it. It can also control thermal management systems. We can integrate heaters into our BMS units, and that allows our batteries to actually heat the shelves on which they're placed. And we'll talk just briefly about that later, a heater solution that we have. But the main purpose of the BMS is to protect the battery from damage and ensure that it has access to its full capacity and it lasts for its full life. So a simple example of a BMS is shown in the top right corner here. There are connections for the battery positive and negative, and these are individual cells that you see here. So what the battery management system does is towards the end of the charging cycle, it makes sure that these cells are balanced and that all of them reach a full state of charge. And so that charging through from one cell to the next, if they ever get off in their states of charge, what can happen is we can balance it with these individual charging circuits. So most people are not that familiar with BMS systems because most of our batteries don't have them. Lead acid batteries, a typical car battery, does not have a BMS, right? And really, it doesn't need one. It doesn't need one because you don't have as many cells. These are typically, there's a 6-volt battery there. Typically 12-volt batteries is very common. And so it is the case that lead acid batteries run in series can get out of balance, and so some more sophisticated systems would keep balancing equipment. Well, all lithium batteries have to have a BMS system. Even if you tear into just a very small piece of electronics with a very small pouch cell, like a dog collar or a Bluetooth set of headphones, there will be a small circuit there that has a BMS that regulates the charging of that battery. Currently, my phone BMS system is out on the charging board, but I do still have a wireless charging. And so these things, they're there for all lithium batteries, and we're going to talk about the variations and really the high-end BMS units and what they can do. So again, they're there to protect that battery, also to help prevent that thermal runaway that I was talking about earlier. So an analog BMS system is really like a pre-programmed BMS that you can't really make changes to it afterwards, but it allows for simple balancing of cells. And it typically, again, programmed during manufacture. It's got integrated components, of course, diodes, controllers, but again, less sophistication in terms of the communication and the variations that you can do with these. Its performance is typically based on electrical signals. It relies on values of the components to take action, such as opening up switches, etc. And it doesn't transmit data like communication, which is what we're quite interested in. Here's an example of a different BMS. This is not a AmpliPHI BMS, not a Briggs Stratton product, but this is a BMS I had bought from Overkill Solar. It is rated in terms of its maximum power capacity. It can handle a current of 100 amps. It's a 16S 16 series, so that is designed for LFP. And it's also a 48-volt system. What you can see here, all these wires that are coming down, these are balancing wires, and these are used to balance the cells. This is also a programmable BMS in that there's an antenna here. It's got Bluetooth connectivity. This is a Bluetooth module here, and it allows us to program it. So a BMS like this allows us to set different communication, to do communication and set different values into the cell if we want to vary it. So these allow us to reprogram. It allows us to take digital input and convert those electrical signals into actions, right? Using software, especially external, if we have communications like this one with Bluetooth. And it may or may not transmit data to external equipment. If you have the appropriate communication, such as ZAN bus or CAN bus integrated into the BMS, then like our batteries do, then you can communicate with external equipment like a gateway or like an inverter. Batteries with digital BMSs may also have an analog BMS as a fail-safe. So if the communication and the device gets damaged or communication loses for some extent, there's typically a default that these digital BMSs will go to. So
Nathan, a question. Philip's asking again, and I think this is kind of a multi-part question, so I'll go ahead and read it. How many cells have to have an issue before the battery management system shuts the battery down? How does the technician know there is an issue since there is no idiot light in assuming the breaker has not tripped? Presumably, an individual battery will show 0 volts. And Philip's mentioning, not all inverters allow comms. So
yeah, it's a good point. So if you have a battery in a large bank and it doesn't have communication, let's suppose you have 16 batteries in parallel, you often might not have any indication that that particular battery is not functional, right? And that argues for using communicating batteries, right? Knowing that there is, that the battery is not charging or discharging, for example. And so there are two different questions. There's one is how many cells have to go out, which would be internal to an individual battery module. But knowing whether a battery module, a full battery itself in a bank of batteries goes out depends on that specific battery. For instance, this battery, if it was non-functional in a system, you would see that it's communicating outward, that it's not discharging, right? It might be giving you a warning, like an over temperature condition, etc. So I can't give you a quantitative answer of how many cells inside a large battery pack. Like, for instance, this battery here probably has on the order of 200 cells in it. I think we're around 20 20 parallel, 16 in series, so more than 200 cells in this battery. So I can't give you an exact answer on that because, frankly, I just don't know how many cells have to go bad before something like that happens. So that's the best I can do on that one. I appreciate the question, and please keep them coming. We have a whole range of battery offerings, and I'm going to point out we have our low voltage batteries, which are PHI, our AmpliPHI, our SimpliPHI outdoor battery, and some other smaller format batteries, as well as new ones that are coming out that operate at low voltage. What we mean by low voltage is typically up to 48 volts, like 12 volt, 24 volt, 48 volt batteries. And then we also have high voltage stacks. So typically for large battery systems, it makes sense to go to high voltage because you're moving so much current at low voltage to produce the same power. One way you can avoid having to use enormous wires, right? 500 kc mil, for instance, would be to increase the voltage and decrease the current. And so we have also a whole battery offering, our high voltage commercial and industrial battery offerings. These go up to around 1200 volts, and these uses at the top of each of these battery stacks is the equivalent of a BMS, something called a stack controller. And then on each of the individual battery modules, Daniel, it's 4.3 kilowatt hours per module. Is that correct?
Yep, correct. And they either can come in 24 or 48 volt stacks.
Yes. Yes.
Individual modules.
And if you have a 48 volt stack, you would need 2 stack controllers. So the 24 volt is a little bit more economical, but it doesn't get to quite as high a voltage. So we're limited in that. And each of these individual modules communicates as well through something called a cell interface. And so those communicate with the overall stack controller. And so if you're interested in these, we don't spend as much time on it here, but we certainly have these offerings. And so we can talk to you about them or put you in touch with the team that works on the commercial and industrial packages. And we'll talk a little bit later about some of those inverters that are 3-phase, 480 volt, 208 volt, etc. Of course, you can do those with low voltage batteries and inverters as well. But let's move into how cells get balanced inside a battery module. There's something called passive cell balancing. This is a very low-cost way that those cheap, the low-cost systems, BMS systems, would use for balancing. It uses a resistive element, and if you imagine a charger being put across these 4 cells here, you could imagine current flowing straight down through the chain like this from positive to negative. But if one of these cells, let's say cell number 2, fills up before the others, it would prevent cell number 1, cell 3, and 4 from actually charging. So a way around that is to have a very simple resistive circuit in which you allow a little bit of current to bleed through a resistor and charge up a capacitor and bypass that actual cell. The problem with that is you can, of course, go around, let's say we go around cell number 2 through this resistor. You can go around through that resistor and then get to cell number 3 and 4. But doing so, you have to pass through these resistive elements. And what a resistor does is it creates a voltage difference, and it slows down current by basically turning the energy and some of the energy into that electrical current into heat. And so it's not an energy efficient way to balance cells. But for often low-cost devices like a Bluetooth set of headphones, you don't care about having the system be 80% efficient versus 99% efficient. So this passive cell balancing is not a great solution for larger battery applications where we really care about that round-trip efficiency. So a more sophisticated way of charging the batteries, and the way that we use of charging the batteries with our BMS, is to do active cell balancing through what's called charge shuttling. So charge shuttling, imagine that I've got a charger hooked up and it's charging cells 1 and 2. Well, if cell number 2 fills up, it would prevent current flowing through cell number 1. But what you can do is you can have a switching device that's constantly switching between connecting the top cell to a capacitor and the bottom cell to the same capacitor. If we connect the top cell to the capacitor with the switches in the position they're shown, the capacitor would charge up to cell number 1. And then if we then switch both of those switches simultaneously to the lower position, that voltage that was on cell number 1 would then be connected to cell number 2. And if cell number 1 had a higher voltage, higher state of charge, the excess energy on that capacitor could be delivered to cell number 2 with very little to almost no energy loss. So this is called charge shuttling, and this is a energy efficient way to keep that balancing. So this balancing typically is happening at the very end of the charge cycles, those last moments of the charge cycle. And for that reason, it is important to occasionally get your battery modules to a full state of charge. So it's not great. It's not a great idea to operate your battery modules between, let's say, 20 and 75% state of charge continuously. You want to, yes.
Christopher's asking, and I'm not sure if I understand this. What is the time sample rate Briggs & Stratton battery management system interface with SCADA, SCADA monitoring for remote troubleshooting for commercial and industrial applications?
It's a great question, and unfortunately, just like Daniel, I don't know. I know with our low voltage, we're continuously doing that, and I think the time sample rate is on the order of 30 seconds. But I could ask our IoT guys and get back to you. Daniel, if you don't mind collecting the contact information, let's put him in touch with the head of our high voltage team and get that information to him. So thank you, Chris. Sorry, I don't know the answer. Proper programming for non-communications batteries. So we do have a non-communicating PHI battery, and it allows us to give you an offering at a much more competitive cost without having to, sacrifice the quality of the cells. We have a same high quality cells inside these PHI batteries as inside the AmpliPHI and the SimpliPHI, the communicating batteries. We just don't, it's a much lower cost BMS. And so it's a non-communicating product that we offer. It doesn't mean it's not a good battery. It might fit the needs of a customer or a particular installation. For instance, many of these batteries have been used. It's a very popular battery around the world. And these PHI batteries, can be chained in large numbers of these batteries can be chained in parallel to power systems. We have a Hawaii example. We've got an airport with, I don't know how many batteries, hundreds of batteries in parallel. We have hospitals using many of these batteries in parallel, and they don't care about communications. Now, you can individually go back and test battery modules by isolating them using the breakers. And if you don't have the opportunity to do that, you can even pull it out of the system. And I mean, that goes to answering the previous question from before. One of the ways to know if a battery is functioning, if it has an issue, is to turn the other batteries off that it's paralleled to and just check an individual one, make sure its voltage seems normal, draw some current from it, make sure that the battery is not heating up, etc. That being said, with this non-communicating battery, you can always buy external equipment. So what I'm showing here on the top right, this is a Victron BMB712 smart battery monitor. The smart with Victron means that it's Bluetooth. It'll interface with a Bluetooth app you can have on your phone. I in fact have that Bluetooth app on my phone, and it's excellent. This is a temperature sensor here, and so you could put this on the outside of your battery. Not quite as good as the integrated temperature sensor our other batteries have. We have multiple thermistors inside of our other batteries, the communicating batteries. But you can put this on the outside of the battery, and you can trigger the system to react to that temperature. I'm showing the Schneider Connect SCP as well, and you can do battery settings and monitoring with external equipment. And so depending on the situation and the environment that your battery's in, you might want to purchase compatible equipment like this to use with non-communicating batteries. For communicating batteries, if you have communications, you will need to have the wiring done for your closed loop. And so a closed loop means that you essentially have all of the batteries connected to each other, one to the next. And so I'm showing here in series how you would connect 4 AmpliPHI batteries, for instance, to let's say a Solarc inverter. And so you would do that. You could put a terminating resistor. You never want to have an open port. And so I'm connecting battery 1 to battery 2, but battery 1 would have an open port on the BMS side of the battery. And we close that off with a terminating resistor. And what that terminating resistor does, it's a little, I think it's a 120 ohm resistor. And what it does is it just shorts out 2 of the pins and says, hey, I'm the end of the chain, right? It lets the BMSs know that this is the last battery in the loop. And so you never want to have an open port, and so you should have terminating resistors at the end. Additionally, there is a device port on these batteries, and with the SolArc, you would use that device port to connect the battery directly to the SolArc inverter. There's a CAN bus port on SolArc inverters, and then that SolArc can react to the requests of the battery, so the battery can automatically request changes to the charge rate. For instance, the AmpliPHI battery, if it gets cold, it can slow down the charging rate to protect the cells. And in fact, our BMS has a fairly sophisticated code that allows this battery to operate over a much broader temperature scale than most of our competitors' batteries. And so what's shown here is connecting properly the closed loop communications. One big loop, all 6 of these batteries. It's also showing the combining of these batteries. And so you can see that we're pulling power off of opposite corners of the battery stacks, and we have these 2 battery stacks in parallel. We never run our batteries in series. And so showing both of those as an example here, it's important that we keep our batteries balanced, both with the external connecting equipment as well as the BMS units inside doing that. Here I'm showing a stack controller, and this stack controller is for a 48-volt battery modules. I know that because there are two stack controllers on top. Sorry, I'm showing a high voltage stack. This is server rack mounted batteries that we have, and typically these are put in things like shipping containers that have HVAC systems built into them to maintain optimal temperature. And so we have offerings like that if you're interested in backing up a large system like a hospital or like a industrial building, for instance. We can provide large solutions like that, so please let us know. What's shown here is an Oztec a high voltage 3-phase inverter. Also, I think, is this the 30K, Daniel?
Yep, 30K.
So SolArc came out with a new 30K and 60K, new 30K and 60K inverters. This product, the 30K unit, operates at 208 volts. So it's a 3-phase units. The 480 3-phase units are the 60K units. And so capable of 480 service for this and the 60K SolArc, and then the 208 for the 30K unit. And we have solutions for those if you're interested in large systems. Let's talk a little bit about the batteries, the terms that we use for batteries that you probably hear a lot, and you may know them already. So again, we mentioned before energy capacity. That's how much energy a battery can hold, typically specified in kilowatt hours. And that's actually specified at a certain temperature as well. So under low temperatures, you'll get less energy out of batteries. So you get the most energy out of your battery around 40 Celsius. The kilowatt hour rating of a battery is typically done at 25 Celsius. It's a full discharge cycle at ambient temperature at 25 Celsius. And that tells you how much energy your battery will hold and deliver. The current capacity of a battery is how much charge the battery can deliver. So if I start discharging a battery and I monitor how many amp hours are in there, or how many electrons actually move from one side to the other, that's a monitor of the current capacity. It's really no different from counting how many actual electrons will go from one side to the other. That's current capacity. That used to be used as a specification of a battery capacity, and that made sense when all batteries were the same 12 volts, right? So somebody can have a 225 amp hour 12 volt battery, but if you're comparing that to a, let's say, 100 amp hour 48 volt battery, well, a 100 amp hour 48 volt battery has a lot more energy in it, right? Because energy is current times time. So we don't really use amp hours that much anymore. Oops, didn't mean to click on that. Next term is nominal voltage. So nominal means nameplate. It's also a term that suggests the voltage of the battery at a 50% state of charge. Voltage of a battery varies as its state of charge increases or decreases. And so as the state of charge of a battery increases, it gets more full, the voltage goes up. And so nominal voltage can be used. I used it earlier to specify a single cell is 3.2 volts nominal. So if you multiply that times 16 cells for series, you would get a nominal voltage for a 48 volt battery is actually closer to 51.2 volts at a midpoint for its state of charge. So you might hear that term. We often have 48-volt batteries. And the reason that's important and why I mention it to you here is when you're buying equipment, like, so let's suppose you want to use a switch. You don't want to use a switch that's rated to 48 volts for a 48-volt nominal system, right? The state of the voltage of a 48-volt system could go up to 58 volts. 56 volts would be 100% state of charge for us. But if you overcharge a battery, you can get to higher voltages than that. And so you want to make sure your equipment is compatible up to the maximum voltage range of your batteries. Next term to give you is C rate. And this one is important because it's very common now. C rate is a measure of how quickly the energy that's stored in the battery can be delivered. So I'm showing here another example of a water tank. This is a water tank up on a roof. Given these pipes, how quickly do you think we could fill up or discharge this tank, right? If we try to do it too fast, we could, of course, burst these plastic pipes. A battery has internal wiring. It has components internal that could overheat if we try to do it too fast. And so for energy storage cells, the numbers are typically C/2, C/3. And what that means is we can fill up the battery in 2 hours, or we can fully discharge the battery in 2 hours. That would be a C/2 rating. The capacity of the battery in a number of hours. So a 5 kilowatt hour battery divided by 2 hours would be C/2 in terms of how quickly it can deliver. So 2.5 kilowatts would be the rate. Again, our competitors, most competition is somewhere in the C/2 to C/3 range. Most people don't want to discharge their battery that quickly, but they would like to be able to charge it quickly, especially if they have a generator. They want to run that generator the least amount of time. So keep in mind when you're using our batteries, all of our batteries currently are rated at C/2. You wouldn't want to charge them faster than 2 hours. And that's the same on the discharge rate. You wouldn't want to discharge it faster than 2 hours.
We've got a question, Nathan.
Yes.
Fred's asking, what's the rule of thumb to add new batteries to existing energy bank without compromising performance?
It's a great question, and I'll give you the runaround. It depends, but to give you a rough rule of thumb for moderately used battery bank, meaning it's not undersized, we typically say about 3 years. Right. Let's suppose I have a battery that's paired, a 10 kilowatt hour battery bank that's paired with a 3 kilowatt inverter. Right. That's what I would consider moderately sized. The battery bank is capable of 5 kilowatts output, C/2. So 10 kilowatt hours divided by 2 hours would be 5 kilowatts of output. But you're only using 3, so that battery is not heavily taxed. And so about 3 years in that condition. If you had a battery, a 10 kilowatt hour battery, and you were running a 5 kilowatt inverter and you were doing it frequently, you would be heavily taxing that battery at the C/2 rate repeatedly, and then the battery will age faster. So the reason we don't want to go into an old battery bank that's undersized and go in and add multiple new batteries is that the degraded older batteries will do less of the work, and they will age the newer batteries faster. So my recommendation is if you've got a system that was normally sized and you have used batteries on it and you want to upgrade the system, if it's beyond about 3 years, or let's say maybe stretch it to 4 years for a lightly used system, I would recommend selling the used batteries and buying new ones because you would get more value out of them. I also have to point out that if you have used batteries and you combine them with new, it decreases the warranty on your new batteries to the expiration of the old batteries. And that's because the old batteries age the new batteries faster. So rule of thumb, about 3 years, maybe 4 years for lightly used batteries. Great question. So choosing the right product and BMS. So first off, we have a huge variety of offerings, from these high voltage stacks in this HVAC enclosed shipping container, a 20-foot shipping container with lots of server rack mounted batteries interfacing with a high performance 3-phase 480 volt inverter, to smaller mobile units like this one We also have, for those of you that are, maybe interested in those faster installs, we have kind of a plug and play solution. This is a Solar, I think that's a 8 or 12K here, in one of our, what do we call, access cabinets. And this comes ready to wire. Everything is included. You've got your bus bars ready to go. Those bus bars connect to combiners that are here. The wires are sized for you, so you can just order this full access cabinet, pop those 6 batteries in, and the inverter comes pre-programmed, ready to go. If you want an EMP, electromagnetic pulse hardened inverter, to protect it from lightning storms or an EMP attack or any reason, right, we can get that as well. And so we do sell EMP hardened access cabinets, which are pretty much plug and play. It's about the easiest install you can do. And it's also got a nice look, and it's in a NEMA 3R enclosure, which is outdoor rated. So keep that in mind if that's a product that. We also have, of course, our lineup of batteries, the PHI batteries. We have a small format PHI battery. We have the AmpliPHI and AmpliPHI batteries as well. So let's go into the batteries that we offer. So we have the smaller format batteries we have come in some small sizes down to 0.73. I believe it's a little bit bigger than that. I'm not sure on my number here. I thought it was 0.76, but a small battery. This is great for mobile uses. We have many of these that are used in, for instance, with mining lights, etc. A slightly bigger version of this is 1.4 kilowatt hours. Again, that could provide power of about 750 watts output. This is great for mobile applications. And so we get people using these things for things like travel vans or small lighting systems that you want to use for maybe work lights. So we got our start. AmpliPHI got their start in the film and the film business, really providing power for film equipment. We have the PHI battery comes in 3.8 kilowatt hours. I believe it's 3.86 kilowatt hour sizes, both in either 24 volt or 48 volt. So the 24 volt version has 8 cell stacks in series. The 48 volt has 16 cell stacks in series, both containing the same amount of overall energy, but one delivering more current for a longer period of time, the other delivering less current, but at a higher voltage, double the voltage. So the same overall energy. This is a UL 1973 certified product. Again, it's got a surge rating on it. A very high quality battery. It's about 86 pounds, so it is fairly heavy. But for mobile home-based applications, it doesn't matter that much. We have cabinets that it can fit into, wall brackets, etc. And so it does fit into our existing cabinets and can be used for our ESS. This is our AmpliPHI battery. It's got that more sophisticated communicating BMS that's in there. Allows you to communicate with compatible equipment like a Solar inverter or a Briggs Stratton inverter. It's got the integrated breaker as well. And this battery comes again in the same overall capacity, 3.86 kilowatt hours at standard temperature. You can parallel up to 60 of these. I believe I've got 72 on here, but that has to do with the lengths of the communicating equipment. So if you have your batteries far apart from other equipment, you'll have to keep that in mind when you're trying to get an overall size of your equipment. This is an outdoor rated battery. So the big difference between the AmpliPHI battery and the AmpliPHI battery is the NEMA 3R enclosure for this battery. So you've got a battery that's waterproofed. A nice feature of this battery is that the terminals are actually offset, so you can run big 4-aught cabling straight across from one battery to the next when they're in line on a wall. And then for outdoor installations, we recommend including the conduit cover box, and it's a nice closed look on this system. You can connect those batteries through the knockouts on the conduit boxes. Bigger battery, 180 pounds for this battery. It's wall mountable. Of course, it's compatible with our inverters and the Solar, etc. Here's another view of the battery cabinet. So when you're doing outdoor installs, if you're not using that 4.98 kilowatt hour battery, we would encourage you to, of course, get a NEMA 3R enclosure. We do make and sell them. These have built-in fans that turn on if the temperature exceeds a certain limit. I think it's 110 Fahrenheit that the fan will turn on and cool. Batteries do give off a little bit of heat not like inverters do, but they give off a little bit of heat. You can also, of course, like I said, program that, include that solar inverter inside this cabinet. We call that the access cabinet. If we do that, it takes up the space of 6 of the batteries, and then we only have the opportunity to go to up to 22.8 kilowatt hours in this outdoor rated enclosure. But in a 12, in an enclosure, we call this the Boss cabinet, a Boss 12, because it can include 12 of our batteries inside, and you get up to 45.6 kilowatt hours in that. That's a pretty large battery backup system. Let's talk briefly about charging. The batteries, when they charge, go through a 3-step charging process. And I'm sorry, I'm not sure what happened to this image here, but the 3-step charging process is a bulk charge, and that bulk charge is followed by an absorb charge, and that absorb charge is followed by what we call a float. So let me explain those three. The bulk charge is a constant current process, and so when a piece of charging equipment begins charging batteries, you will not be observing the battery's voltage anymore. You will be observing the charger voltage, right? So you'll see the battery voltage go up to the charger's voltage, and that will start driving charge into the battery. As that battery receives charge, the voltage of the battery bank will go up and up and up. And for our batteries, we top this out at 56 volts. So we go constant current at C/2 for our batteries until we reach 56 volts. And then we just hold it at 56 volts. So that's the absorbed part of the cycle. So a constant voltage, so 56 volts for 6 minutes. So we do that for either, if you have charging equipment, you can either set it to 0.1 hours or 6 minutes, same amount of time, right? That's the absorb. When the battery gets to this absorb cycle, it's already about 90 to 95% charged. A small amount of energy is delivered during the absorb cycle, in which the current drops down. And once that current either reaches 2% of the overall amperage of the battery bank, or we get to a time of 6 minutes, that ends the charging cycle, and we consider our battery 100% charged. It's at least 99% charged at that point. So the bulk is probably about 95% of the charging, another 4 or 5% during the absorb cycle. And then that battery, if you have it set to float, because you have extra energy from a renewable source, you could just float the batteries at 54 volts constantly, and that'll just keep them topped off.
Question, Nathan.
Yes.
And this is a direct one if I've ever heard one. Philip's asking, has any AmpliPHI 3.8 48 volt battery sold ever caught fire? And if so, what caused it? And maybe you could speak a little bit to our UL 9540A testing.
That's a good question, and I think I should just answer honestly. I don't think we've had battery. It depends on what we mean by fire, right? We have had batteries go into off-gassing thermal runaway events. However, the reason that this has happened is we've had external equipment fail. So there is a inverter, I'm not going to name, or sorry, a charge controller, I'm not going to name company names here, that when fails in the closed position and can deliver extremely high voltages to batteries. And so it is possible to get a battery, right, to have problems if you damage the battery. Now, overall, our battery management systems do an extremely good job of protecting our batteries, right? And they cut off our batteries from external events. But there have been instances, there are very few and far in between, when we've had other people's equipment fail, which has caused off-gassing events. We have an extremely good safety record. And one of the reasons that we do so much heavy testing on our batteries is for safety. It's our #1 priority. We can't beat on cost compared to some of the low cost, frankly, cheaper equipment that's coming in from Asia. But what we can do is provide higher quality. And that's one of the reasons people buy our batteries, is our safety rating. And you can go in and look at our 9540 safety tests. We publish them, and we encourage our competitors to do the same, because we are quite proud of our safety tests. So I hope that answered the question. And I encourage you to look at our 9540 safety tests.
And Nathan, I just want to add,
Yes.
maybe build to that. When you say that the battery management system will cut off our battery, what do you mean by that? How does
We
the
will
battery
open up a
disconnect?
contactor. And I think I also have to distinguish that that has not happened with our AmpliPHI and our SimpliPHI batteries, right? Our newer batteries, we've never had one of those issues. And so those batteries with a more sophisticated battery management system, again, can protect themselves in a very effective way. And so that's another reason why we've developed such a comprehensive BMS system, is to protect for safety, because it's our #1 priority. So great question, I appreciate it. This is also showing the discharging characteristics. And notice that the ratings of these batteries, that C/2 rating, is there for the charge and the discharge. Let's look at the battery state of charge versus voltage. And I realize we're running out of time. I might go a little bit quickly through this just to be able to deliver this information to you, but I do think this is important. When a battery is in a charge cycle, you can see I have current coming into an individual cell as green here. The charging equipment that is pushing into the battery, is pushing charge into the battery, has to be at a higher voltage than the battery. So when a battery is in a charge cycle, the charge that you see displayed by the inverter or the charging equipment is a voltage above the battery, right? And typically you'll see that voltage go all the way up to 56 as that process is completing. So keep in mind that when a battery is in a charge cycle, the voltage is higher than the resting voltage of the battery cell. If the battery is discharging, current is flowing out of the battery cell. Notice I've drawn a little resistor inside this battery cartoon here, and that resistor is there to identify what we call internal resistance. Resistance from the current flowing through the cells, resistance of the connecting wires inside the batteries, the nickel connectors. And so when you are discharging a battery or charging a battery quickly, you have a greater voltage across the internal resistance of the battery. And the overall voltage that you see on your charging equipment would be connected outside of the battery, would be the voltage of the resting voltage of the battery cells plus the voltage across the resistor. So in a charge cycle, you see a higher voltage. In a discharge cycle, you have a voltage drop across this resistor, you see a lower voltage. I mention that because it's pronounced in colder environments. The internal resistance of the batteries go up in cold environments because the electrolyte gets a lot more viscous, and it's quite a drastic effect, and I'll show it to you here in a minute. This is a state of charge for a resting battery. It shows you what the approximate voltage is you should see on a battery that's 99% state of charge, would be about 53.2 volts. And then as you discharge that battery to lower states of charge, you'll see that voltage drop. At about 50% state of charge, a resting battery will display a voltage of just over 52.4 volts. And then eventually we get down to a point where the battery voltage drops off fairly quickly. At a 10% state of charge, we're down under 51 volts, and we can go all the way down to 48 volts without damaging our battery. That's 100% discharged. Now, this is resting. This is when the current going into or coming out of the battery is 0. If I'm discharging at faster rates, remember I was just giving you values for what the state of charge of the battery is, its relationship to voltage. Well, again, when we're discharging the battery, we're losing some voltage across here, and so the displayed voltage on the inverter as the battery is discharging will be below the resting voltage of the battery. So I point this out because here I don't have the resting curve on top, but it would sit higher up. If I'm discharging the battery based on state of charge, I will get a greater drop below that rate. So if I'm discharging very slowly at a C/5 rate, that means over 5 hours, and in my opinion, that would be a typical discharge rate, you will see a curve that looks like this. But if I'm discharging even faster at the same state of charge, let's go to 50%, I would see my voltage be on the order of a volt lower. If it's colder, this separation will be even more, right? So you can lose some voltage. And so what I'm showing you here is some data taken by a student. I've kind of artificially given it here because we were actually only discharging single individual LFP cells. This is not data from a SimpliPHI battery, but it is from an LFP cell. And what you can see is when the battery cells are held at a fixed temperature, the voltage of that battery at the same C/2 rate. So I'm discharging this battery so that it discharges completely in 2 hours. You can see the voltage drops significantly, especially as I get cold. So once I get below that 15 degrees Celsius, I lose a lot of overall capacity. That energy is still there in the battery. The charges are still on that anode side ready to go to the cathode side, but I'd have to heat it up in order to get to acceptable voltages. You can see that if I had a battery at 0 degrees Celsius and I was discharging it quickly, I'd hit my 48-volt low battery cutout when the battery is still at a 75% state of charge or a 25% state of discharge. So keep that in mind. If you store your batteries in cold environments, you're going to have less usable energy in them at fast discharge rates. If you discharge slowly, it shouldn't cause as much of a problem. These curves wouldn't be much below, but this is showing resting voltage on the top versus increasing same discharge rate versus decreasing temperatures here. So what can you do in cold temperatures? Well, our batteries, the BMS system is there to protect these batteries in cold temperatures. And one of the things that we can do with that battery is change the charge and discharge rates. I'll come to that in a second. I just want to point out that atmospheric humidity by itself doesn't pose a threat to the batteries, but if you're in high salt areas, you would want to keep these batteries, especially out of a direct exposure to salt water that could be in the air, for instance. So keeping them inside a NEMA 3R enclosure is a good idea. It prevents that salt condensation on the batteries, which can cause corrosion. Cold temperature installation is a good idea to keep your batteries inside an insulated enclosure if possible, and potentially even offer some heat. You might get more usable capacity out of your batteries if you use some of the energy in the batteries to keep them warm. So we do have a solution for these cold temperatures, and we can integrate this if you call us in advance. So if you order your batteries from us in advance and say that you want a heating pad solution, we have the ability to integrate a heating pad controller into the battery BMS system, so it turns the pads on and off automatically. And so if you're in a cold weather environment, I'd encourage you to talk to your representatives, your sales representatives, about a potential this as a potential solution. Also, of course, you can use insulation, but for our non-communicating batteries, the ones with a simpler BMS, their operating range is from 32 Fahrenheit up to 120 Fahrenheit on the charging side, and on the discharging side, you can discharge them from -4 Fahrenheit, -20 Celsius, this is very cold, right, up to 140 Celsius. When you're discharging the batteries at cold temperatures, it doesn't take long for the battery itself to warm up and for you to get more overall capacity, unless you're discharging very slowly in very cold temperatures. So keep these temperatures in mind. You are going to have to protect your batteries from charging below freezing in cold environments. Well, the AmpliPHI and the SimpliPHI battery have, as you can see, a much broader operating range. And the way we do that is the AmpliPHI and SimpliPHI batteries, with their more sophisticated programming on their computer, their BMS, can control the charge rates. They can request different charge rates from the charging equipment, communicate out that, hey, when I'm below 0 degrees Celsius, charge me at a slow rate like 3 amps. What that does is it starts to heat up the cells and allow you to increase the rate at which you're operating the battery up to that optimal range from 7 to 50 degrees Celsius. And so it gives a way for us to deal with cold weather. And then there's fault protections, of course, built into these batteries, which will turn it off if it gets too cold, or turn it off if it gets too hot above 60 degrees Celsius. Okay, so those rates are given here. If you're interested in both the AmpliPHI and the SimpliPHI and our newer battery products, will have these controls built in. I'm going to skip these slides here. I do want you to consider sizing your equipment properly. Remember that when you are using operating equipment, that the batteries themselves have power limitations on them, and so you'll want to make sure to program the rates appropriately into your equipment. Also, just want to point out that DC breakers have trip times, and it's important to consider those when you're using these to protect batteries and cabling. Our inverter has a 200 amp fuse built into it, an ATC fuse built into it. Our batteries have breakers built into them, but if you want to make sure you're using the right size cabling, et cetera. And I highly encourage you to include DC disconnects in your systems. Here's a nice example of a couple of solar arcs that are paralleled up here with AmpliPHI batteries. You still have to do proper programming, especially if you're not using a BMS. But of course, there's some programming in the commissioning process. Here's a nice example in which somebody has a wind system, and this is a load limiter. You can see an example here in New York City, where one of a few battery companies is approved by the New York State Fire Department, or New York City Fire Department, to use our solutions in high-rise buildings there. And so you see 3 of the Boss 12 cabinets, as well as a couple of our customers. So Daniel, can you tell us about a couple of promotions here as we wrap up?
Yeah, really quickly. So anybody who's on this call, you can qualify for some of these rebates. One of the most exciting ones is if you do an install of our first energy storage system, battery inverter, energy track gateway, we're going to give you $1,000. The next one available to everybody on this call is when you purchase one of those 4.98 batteries, they have it's an outdoor rated battery, and we'll give you the free conduit box, which is the weatherproof enclosure on top. Additionally, for everybody on this call, we have buy 5 batteries, and you're going to get 1 free battery with the purchase of that Boss 6 cabinet. Those are those NEMA 3R cabinets that we showed you earlier. One that's only available to IQ installers, and if anybody's on this call that's interested in becoming an IQ, we're going to have on this next slide, we're going to have a link or a QR code to become an IQ installer. $100 back, and this promotion is running all year long. That's right, $100 cash back rebate for every battery purchased. You have to apply on a form on our website, and we're going to send you that cash. Nathan's already talked a little bit about the S-chip incentive, so I'm not going to talk much about that. But keep in mind, we want to reward everybody for working with us, and these promotions change. There's always new ones coming, so stay tuned.
Good, thank you, Daniel. And if you're not an Elite IQ installer, we encourage you to apply to be one. Reach out to Daniel or myself if you're interested in that program. You install 25 batteries in a year, you just do a few systems for us, we'll send you a check for $2,500. So keep that in mind. It also puts you on our map. It allows you to be found by our customers that are looking for installs. If you're here for the NABCEP credits, I want to direct your attention to the email here, training@ampliphipower.com or training-oxnard@basco.com, briggsandstratton.com. So please reach out to us by email if you're looking for those NABCEP credits. It normally takes me about a day to generate those certificates. I typically wait for everybody to get those in. So please let me know if you're here for those NABCEP certificates. We'll get them issued. Again, thank you for joining us. Thank you for your attention. Thank you, Daniel.
Thank you, Nathan. Take care, everyone.
Bye, everyone.